Hello everyone. Welcome to the live problem solving session for week 10 of the course Computational Computative Algebra. So first let's summarize the topics of week 10. Then we will solve some problems based on those topics. So which will help you to do the uh, assignment problems. Uh, in week 10, we basically exploring the properties of graded rings. So we started with Z graded rings. Uh, and we have seen when we have a Z graded integral domain, then we know the structure of that graded domain. Structure of a Z graded domain. And after that we studied some properties of the graded rings in terms of dimension and other things, and basically the graded version of some standard results like Nakayama's lemma and height of a prime ideal, all those things. So the support of a graded ring we have already seen. It is a so we have defined the largest homogeneous ideal inside an arbitrary ideal, and using that we have defined we have proved some results like if P is a prime ideal in the support of a module, then the P star, the largest homogeneous ideal inside P, will also be in the support. And we know that associate primes, if M is graded, then associate primes are also graded prime ideals, and minimal primes are also graded ideals, all those things. So support and also dimension of finitely generated graded modules. And after that we studied about the graded version of the Nakayama's lemma, and we have seen some consequences of this graded version. So graded NAC and consequences of this result. So in particular, if you have a graded finitely generated module, then we will have a then every minimal homogeneous set, every minimal uh, homogeneous generating set of M will have same number of elements. So so in particular, in that case, we need the base, the zeroth component has to be field or star local. So those things are there, means those conditions are there. But we have nice consequences of graded NAC. So in particular, the result holds for a Noetherian local ring, and the result hold for a n-graded ring where R naught is a field, are somewhat analogous. So so these theories are parallel. So that is what we have seen. And after that we have defined the Hilbert series, which is basically the generating function of the Hilbert function. So Hilbert series of a graded module and we have defined this and also studied some theorems related to Hilbert series, like additivity of Hilbert series and all those things, which is important. Then we have defined the multiplicity of a graded module. So multiplicity of a module. So this is the Hilbert multiplicity, and there is also one notion of Hilbert-Samuel multiplicity. If we have a module over a Noetherian local ring, then we can define the Hilbert-Samuel. But in the graded case, we just define the multiplicity of the Hilbert multiplicity. So these are the topics, or maybe I will write here as graded module. Then it will be clear from the context. So these are the topics of week 10. Now let's do some problems on this based on these topics. Okay, so the first problem is, so let R be a n graded ring R be a n graded ring and E belongs to R be an idempotent element. Be an idempotent element. So recall that idempotent, so E is idempotent, that means E square has to be equals to E. So that is the definition of an idempotent element. So let E be an idempotent element, then show that E is a homogeneous element. So E is a homogeneous element of degree 0. So if in a n graded ring, if we pick an arbitrary idempotent element, then that element has to be an homogeneous element and its degree has to be 0. So we have to prove two things, that it is a homogeneous element, and the second thing is its degree is 0. So let's solve this. So given that E square equals to E, right? And we want to show that E is homogeneous of degree 0, right? So for contradiction, we can assume that, so we'll prove this by contradiction. So assume that E is not a homogeneous element. So suppose E is not a homogeneous element. So E is non-homogeneous element. Let's assume this. So suppose E is a non-homogeneous element. Right? Then we can write down the homogeneous decomposition of E. So then E is basically so E0, the zeroth component, plus let's say ED plus let's say X. So uh, where ED is the least positive degree component, is the positive degree smallest possible positive degree component, or we can write it as ED is the lowest positive degree component. And X is the sum of higher degree components. So we can write E in this term because our ring R is direct sum of uh, n Rn, where n belongs to n, and Rn is the nth homogeneous component. So it's a direct sum. So every element x belongs to R can be written as x0 plus x1 plus dot dot up to xn, finite sum of elements, right? And xi will be belongs to Ri. So because it is direct sum, every element can be written like this. So that is what we are using. So then we have written E like E0 the zeroth term, and ED the smallest possible positive degree term. It may be 1, it may be 2, it may be 3, so it depends. But so we are denoting that by ED, it's of degree D, and all other positive degree terms we will combine them into X, right? Now E square equals to E, that is given because E is idempotent. So it will imply E0 plus ED plus X, and if we take square, it is same as E0 plus ED plus X. Now let's break this left hand side. Then we will have E0 square. So E0 belongs to R0. So E0 square will also belongs to R0 because its degree will not increase. So it is the degree 0 term. So we are separating it as a degree 0 term. Now what is the smallest possible uh, what is the lowest positive degree term in this product? So it will be uh, so we will have two terms. Uh, it will be 2 times E0 plus ED. This is of degree D term. And if we multiply ED square, so then it will be belongs to R2D, right? So its degree will increase. And elements of X are also positive degree, and it's at the higher degree terms. So if we multiply them with itself, we will get more higher degree terms. So we can separate them. So we can write this as plus higher degree terms. So this is equals to E naught plus ED plus X. So I will write this is the degree 0 term, and this has degree D, and these are higher degree terms. So now from both side we can compare the same degree terms. Now comparing same degree terms from both side, same degree elements from both side, we get, so if we compare the same degree terms, what we will get? So degree 0 term here will be same as the degree 0 term in the right hand side. So we will get e0 square will be same as e0, and 2 e0 ed will be same as ed, right? And we will get other relation, but let's just focus on these two relations only. So this has degree 0, these are degree d. Now this so e0 square is equals to e0, that means e0 is idempotent. Now here if we multiply both sides by e0, then what we will get? So 2 e0 square ed is same as e0 ed, but e0 square we can replace it by e0. So this will imply 2 e0 ed is same as e0 ed. And if we take it to one side, we will get e0 ed is equals to 0. Now e0 ed equals to 0. So from this equation, we will get ed equals to 0. So ed is equals to 0. But this is contradiction, right? Because ed is the uh, uh, lowest positive degree term. So we are assuming that it is non-zero. Otherwise, we can merge it. Just it will e is just e0. So this is a contradiction. So what we have assumed is wrong. So what we have assumed is that E is non-homogeneous element. So this thing is wrong. So thus E is a homogeneous element. Right. Now E square equals to E. So that will imply degree of E square is same as degree of E. So degree of E has to be 0. Because degree of E square, we can, this is just 2 times degree of E, right? So this is same as degree of E. So that will imply degree of E has to be 0. So this proves the second part. So in a n-graded ring, if we take an idempotent element, so that element has to be homogeneous and its degree has to be 0. So in particular, okay, I will put that as remark. Okay, here itself. So in particular, if we take the unity element or 1 belongs to R is homogeneous, one belongs to R is homogeneous, and one has degree 0. That means 1 belongs to R0. So this is because 1 is also idempotent. So 1 has to be homogeneous and it has to be it has to be of degree 0. So this is the conclusion of this previous problem. So just remember this, we will use this in the next problem. So let's write down the second problem. So again, let R be a n graded ring, then the zeroth component is a subring of R. So if we take a n graded ring, then its zeroth component has to be a subring of R. And also we can say that and Rn is a R naught module for all n. Okay, so if we take a grade n graded ring, then its zeroth component it has to be a subring of R. In particular, it is a ring itself, and every other component Rn is R naught module. Okay, so let's prove this. So from the so we have already seen that we have already seen or already proved that the one element of R belongs to R naught. That we have proved in the previous remark, right? So so to prove that R naught is a subring, what we have to prove that it is closed under addition and closed under multiplication. So since R naught is a subgroup of R, so this is by definition, because R is a n-graded ring, so its homogeneous components has to be subgroups. R naught is a subgroup of R, it is closed under addition. Right? And also recall that if we take R naught and if we multiply it with R naught itself, then it will be subset of R0 plus 0, which is R0. So this is also from the definition of graded ring, right? Which is basically if we take Rn and if we multiply it with Rm, then it has to be subset of Rn plus m. We are taking n and m both to be 0. So that implies, which implies R naught is also closed under multiplication. Thus, R naught is a subring of R. Thus, R naught is a subring of R. So, for subring, we need to check three conditions, right? That one belongs to R naught and closed under addition and multiplication. These three conditions we need to check for a subring, and that we have already done. So, it has to be a subring. And for the second part, so now for each n belongs to n, if we take an element from R naught and if we multiply with an element of Rn, it has to be subset of R0 plus n, which is basically Rn. So this is the just the scalar multiplication of elements of Rn with elements of R naught. And again we are landing in Rn. So clearly Rn is an R naught module. Okay, this is very simple. So let's move on to the next problem. So in case of graded setup, we used to replace the conditions, usual conditions, by a graded condition. So let's see this. What does it mean? So let R be a n graded ring and and every non-zero homogeneous element and every non-zero homogeneous element in R is non-zero divisor. Then show that R is an integral domain. So what does it says? So in case of an arbitrary ring, if R has no non-zero uh, non-zero zero divisor, non-zero element which is a zero divisor, so R has if R has no non-zero element which is a zero divisor, then R is domain. So that is the definition of an integral domain, right? But in case of a graded ring, uh, we can replace this definition of arbitrary element by just homogeneous element. So that is this problem 3 is saying. So let's prove this. So we want to show R is a domain. So let A comma B belongs to R, B two non-zero elements. So we need to prove that these two elements, if these two elements are non-zero, then their product is non-zero, right? That means they cannot be zero divisors. Then it is sufficient to prove that. So enough it is enough to prove that A times B is non-zero, right? Now A and B are arbitrary elements of R, so we can write down the homogeneous decomposition of these elements, but let's not go into that much details. So assume AI be the uh, least degree homogeneous component of A, be the least degree homogeneous component. Okay, let's write it for B also together. So let AI and Bj be the least degree homogeneous components of A and B respectively. So we can write A as some A0 plus A1 plus dot dot up to AM, and B as some B0 plus B1 plus dot dot some Bn. But so Am and Bn are the largest possible uh, homogeneous components. So there will be some least possible degree of homogeneous components, right? Because A0 B0 must be 0, but some AI has to be non-zero, which has the least possible degree. We are assuming that is AI, and for B we are assuming it as Bj. Now then AI has to be non-zero and Bj has to be non-zero, right? Because they are the least possible degree components. So that will imply these elements are non-zero divisor. So AI times Bj is non-zero. Now, what is AI times Bj? AI times Bj is the least degree homogeneous component of the product. So it is the least degree homogeneous component of the product A times B, and it is non-zero. So this implies the product itself is non-zero because it has a non-zero homogeneous component. So this element has to be non-zero. So in particular, product of two non-zero element is non-zero, and AB are arbitrary element. So product of arbitrary non-zero elements are non-zero. So R has to be an integral domain. So to check a graded ring is domain or not, we need to check that product of non-zero homogeneous element is non-zero. Now let's use this result to prove a result for prime ideals. So it is problem number 4. So let R be a n graded ring and P be an ideal of R. So we are not assuming that P is homogeneous. So P is just an arbitrary ideal of R. So if for all homogeneous elements of R, if for all homogeneous elements A, comma B belongs to R, the product belongs to P implies A belongs to P or B belongs to P, then uh, P is a prime ideal. So P is a prime ideal of R. Right. So to check an arbitrary ideal is prime or not, so then this is the definition for checking an ideal is prime or not. But we can replace this condition AB for general elements to homogeneous elements. So let's prove this. So R, okay. Uh, now P is a prime ideal of R, prime ideal of R if and only if R mod P is a domain. Oh, sorry, we need to take a homogeneous ideal. Oh, okay, PBN homogeneous ideal. Otherwise, this result need not be true. So PBA graded ideal. Graded or homogeneous ideal. So if and only if R mod P is a domain. Now P is homogeneous ideal. So R mod P is a n-graded ring. Now by the earlier result, so this is true if and only if for every non-zero homogeneous A bar comma B bar belongs to R mod P, A bar dot B bar is not equals to 0. So R mod P is a n-graded ring. So it is a domain if and only if every non-zero homogeneous element is a non-zero divisor. So this is the earlier problem. So this is by problem number 3. And if we translate this condition, so this is for every uh, so for every A bar times B bar equals to 0 bar. Okay, so for every homogeneous element, so for every homogeneous elements, A bar comma B bar belongs to R mod P, A bar times B bar is 0, that will imply A bar is 0 bar or B bar is 0 bar, right? And this will imply for every homogeneous element, let's say A comma B belongs to R. So A bar times B bar is 0 bar. So 0 bar means it's a 0 element of R mod P. So that means A times B belongs to P. So this product belongs to P will imply A belongs to P or B belongs to P. That is what the exact condition given in the statement. So all these statements are equivalent. So to check that a graded ideal is prime or not, we need to check only for the homogeneous elements. Okay, so let's move on to the next problem. So it is problem number 5. So let R be a n-graded ring with the zeroth component is a field with r naught equals to k, a field. Now suppose uh, if you take, suppose the quotient r modulo is its nil radical is reduced. Suppose r mod the quotient is reduced. Now let f be a homogeneous non-nilpotent element of R. Let F be a homogeneous non-nilpotent element of R. Non-nilpotent element of R. Now, if R mod, the ideal generated by F, is reduced, then prove that R is reduced and deduce that R is a domain. So the statement is little bit long, but let's recall. So suppose R is a n-graded ring, usual n-graded ring, but zeroth component is a field. Okay, zeroth component is a field, and suppose the quotient ring R modulo its nil radical is reduced. Sorry, so it is already reduced because we are going modulo by the nil radical. So assume that R mod the nil radical is domain. So assume that R mod the nil radical is a domain. Now, if F is a homogeneous non-nilpotent element and okay, let me write this as and the quotient is reduced, then we have to prove that R is reduced. So let's prove this. So recall that reduced means, so what is the definition of a reduced? So a ring, let's say S, is reduced if its nil radical is 0. That means S has no non-zero nilpotent element. So if a ring has no non-zero nilpotent element, then we call it a reduced ring. Reduced ring. Okay. So given that R mod F is reduced, so we want to show that R is reduced. Now, so we need to prove that R has no non-zero nilpotent element. So let's take a nilpotent element and let's prove it is 0. So let R belongs to radical of 0 be a nilpotent element of R. By the way, we are in a graded setup, so we can assume that it is a homogeneous, be a homogeneous nilpotent element. So we can assume R belongs to R naught be a homogeneous. So because this radical of 0 is homogeneous, so let me put this as exercise. So the exercise is I is a homogeneous ideal that will imply the radical of I is uh, also a homogeneous ideal. So this is just a routine check which you can do. So we have taken a homogeneous nilpotent element and we need to prove that R is 0. Now R bar belongs to R mod F is also nilpotent, right? Because R to R mod F, we have a ring homomorphism. So R goes to R bar. So R is a nilpotent element. So its homomorphic image is also nilpotent. But R mod F is reduced. So this will imply R bar has to be 0 bar because R mod F is reduced. So this will imply R belongs to ideal generated by F, and that will imply R equals to F times some S. So this is for some. So R is homogeneous, F is homogeneous, so this S has to be homogeneous. So for some homogeneous element S, for some homogeneous S belongs to R. Now now R belongs to radical 0. So this will imply F times S belongs to radical 0. This will imply F belongs to radical 0 or S belongs to radical 0. Why? Because R mod radical 0 is a domain that is given. And that will imply radical 0 is prime, is a prime ideal. So this is from the property of prime ideal. So either F belongs to radical 0 or S belongs to radical 0. But this will imply S belongs to radical 0 because F is non-nilpotent. But if S belongs to radical 0, then it will imply so so F is an element of positive degree, I yes. So I forgot to mention that FBA homogeneous non-important element, positive degree homogeneous non-important element, FBA homogeneous positive degree non uh, element of positive degree. So homogeneous non-important element of positive degree of R, and this is reduced. So so this R is subset of ideal generated by F times radical 0, and this is subset of R plus times radical 0, because degree of F is positive, so ideal generated by F has to be subset of R plus. This will imply radical 0 is subset of R plus radical 0, and this will imply radical 0 is equals to R plus radical 0. And so by the graded Nakayama lemma, this radical 0 is equals to 0. So this is where we are using k naught is a field, because R0 equals to k is a field. So this is, I think, required for graded NAC, but I'm not able to recall now. But let's assume this. So radical of 0 is 0, and this implies R is reduced, and that will imply R is a domain, and this is because it is given that R mod radical 0 is a domain, and radical 0 is itself 0, so R is a domain. So this completes the proof. Okay, so now let's move on. So let's do some simple problems now. Uh, let's problem number 6. So this is problem number 6. So this is true false. So the statement is every graded ring every graded ring has a homogeneous prime ideal. So this is true or false. So recall that if R is a ring, so in our case, ring means commutative ring. R is commutative with 1 not equals to 0. So then by Krull's theorem, R has a maximal ideal. So this by using the John's lemma, and every maximal ideal is prime. So R has a prime ideal. So in our case, every ring has a prime ideal. Now we want an analogous statement for graded rings, that every graded ring has a graded prime ideal. So this is true or false. So recall that in a graded ring, R, if P is a prime ideal, then the largest homogeneous ideal inside P, which we denote by P star, is also a prime ideal. Is also a prime ideal, right? So this is something we have seen in the lectures. If a ideal is prime, then its largest homogeneous ideal inside that ideal is also prime. So this is one fact. So recall. um, so this is the first thing. Second one is every non-zero ring has a minimal prime. Has a minimal prime ideal. So this is a simple exercise you can try to do by uh, John's lemma, minimal prime ideal. So these two facts I will use. Now let R be a graded ring and P be a minimal prime ideal of R. Minimal prime ideal of R. Then P star is a homogeneous prime ideal of R. Also, P star is subset of P, right? Because P star is the largest homogeneous ideal inside P. But since P is minimal prime, so P is a minimal prime, so P star has to be equals to P. And that will imply P is a homogeneous prime ideal. So P is a homogeneous prime ideal because P equals to P star. So every graded ring has a homogeneous prime ideal. So the statement is true. So this is the analogous statement of the fact that every ring has a prime ideal. Of course, it has to be non-zero. Okay, let's do the next one. So this is problem number 7. So let R be a n graded ring and suppose M is defined by R shifted by -5, direct sum R shifted by minus let's say 8, direct sum R shifted by -9, and let's say n equals to R shifted by minus 3. Then find the degrees of the uh, minimal homogeneous minimal homogeneous generating set. So find the degrees of the minimal homogeneous generating set of the module, graded module of home of m comma n. Right. So here m is 3 direct sum of 3 copies of R, shifted copies of R. So clearly m is 3 finitely generated 3 R module. N is also same, it's just a shifted copy of R. So home of m comma n is also finitely generated. So let's see what is this home of m comma n. So now home of m comma n. So okay, first this is a graded set. So how to see this? uh, so m comma n are graded, so that will imply home m comma n so is also graded. We are taking graded homomorphisms. So how we will define elements, graded elements of this set, or sorry, homogeneous elements? So f belongs to home m comma element is homogeneous of degree, let's say uh, let's say I, if f from m to n is a graded map of degree I. And what does it mean? That means if we take the nth component of n, then it will be subset of the n plus ith component of n. Right? Then it is a graded homomorphism of degree I, and that is a degree ith element of this set, home of m comma n. So in that way, this graded module home is defined. So now we need to find this set, home of m comma n, and m and n are already given. Now how to do this? So let's write this. What is home of m comma n of R? So this is basically home of, so let's write m here, R shifted by minus 5, direct sum R shifted by minus 8 with direct sum R shifted by minus 9. This is comma R shifted by minus 3. Now this is one exercise for you, that home uh, let's say A direct sum B comma C is same as home A comma C direct sum home B comma C. So this is very well known. So let's use this in our case. So it will be home R shifted by -5 comma R shifted by -3 direct sum home. The second one is R shifted by -8. So it will be R shifted by -8 comma R shifted by -3. Again take direct sum with home of the third one. So first one is home shifted by -5 comma R shifted by -3. Second one is R shifted by -8 comma R shifted by -3, and this is the third one, R shifted by -9. So R shifted by -9 comma R shifted by -3. So we have break this thing into three directions. Now here is one more exercise for you, but I think this is in the practice problem sheets, that home of R I comma R j is isomorphic with R of j minus I. So let's use this fact here in our case. Then it will be this one is I, this one is j, so -3. So R -3 plus 5 direct sum the second one, -3 plus 8. R -3 plus 8 direct sum the third one. So it is -3 plus 9. So this is same as R2 direct sum R5 direct sum R6. Now we need to find the uh, degrees of the minimal homogeneous generating set. So what will be the degree? Okay, let me write down it. So we need to find the degrees of the minimal homogeneous generators of the minimal homogeneous generators of this graded module home m comma n. Now if we take R, then it is generated by just 1, and 1 has degree 0. That we have seen in the first problem itself. But what is the degree of 1 here? So now Ri is generated, minimally generated by so it is minimally generated by 1 which has degree -I, because 1 belongs to R0, and R0 is basically the minus ith component of Ri, right? So that is by the definition. So how we shift things? So 1 has degree minus I in R of I. So here 1 has degree minus 2, here 1 has degree minus 5, and here 1 has degree minus 6. So thus the degrees of the minimal generators of home m comma n are, so this is 2 means minus 2 will come here from minus 5 and minus 6. So minus 2, minus 5 and minus 6. So we are using two facts that home commutes with this direct sum, finite direct sum, and how to shift these things. Home of Ri comma Rj is R of j minus I. Okay, now let's do the next problem. So this one is somewhat easier. Problem number 8. So true or false? So the rule dimension of the ring, let's say K x z comma y z comma z uh, not this one. Okay, let's take easier one. So x comma x plus y is 1. So what will be the full dimension of this ring kx comma x plus y? Okay, I need to be more specific. So where x and y are indeterminates over k or variables over k. Okay, now let's try to find the full dimension of this graded subring of kxy. So now, so this is, let's say this is R. Now R is the smallest subring containing x and x plus y. So smallest subring of we can say kx comma y, right? Now, okay, not now again. Since x comma x plus y belongs to R, so that will imply minus x plus y equals to y belongs to R. So that will imply x comma y belongs to R, and that will imply the ring kxy, it's itself subset of R, and R is subset of kxy, and hence R, which is k of x comma x plus y, this is same as k x comma y, and kxy has dimension 2, and dimension of R, which is same as dimension of k x comma y, this is 2, because dimension of k is 0 and we have two variables, so this statement is false. Okay, so we have done this. Now let's do another one. Problem number 9. So it's again true or false. So let R be a n graded ring and I comma j be two homogeneous ideals of R. Then the Hilbert series of R mod I plus j is same as the Hilbert series of R mod I plus the Hilbert series of R mod j. So this is the Hilbert series of R mod I plus j. So this is the notation for Hilbert series. So I am using the same notation as in the lectures. So you don't have to worry about that. So I and j are homogeneous means I plus j is also homogeneous. So this quotient is also homogeneous. So we can talk about the Hilbert series. So these things are same or not. So let's check this. So recall that we have a short exact sequence. It is from 0 to R mod I intersection j to R mod I direct sum R mod j to R mod I plus j to 0. And the Hilbert series is additive. That means Hilbert series of the middle one will be the sum of Hilbert series of the extreme modules. So, thus Hilbert series of R mod I direct sum R mod j of T is same as Hilbert series of R mod I intersection j plus Hilbert series of R mod I plus j of T. Now again, this thing we can split. again Hilbert series of R mod I direct sum R mod j of t is same as Hilbert series of R mod I of t plus Hilbert series of R mod j of t. So why? Because 0 0 to R mod I to this direct sum 0 to R mod I to direct sum of R mod I and R mod j to R mod j to 0. This is also a short exact sequence. So again use the fact that Hilbert series is additive. So if we combine this and this, we will get অতএব or so Hilbert series of R mod I intersection j of t plus Hilbert series of R mod I plus j of t. So or we don't need to use that one. Oh, okay, we need to use that. So this is same as Hilbert series of R mod I of t plus Hilbert series of R mod j of t. So in this equation we have this extra term, and in the question it is just in the left hand side we have just one term, so this need not be true. So this is, in general it is false. If this part is 0, then the result will be true, but that need not be 0 in general. Okay, so this is one problem. Okay, let's do another one. So this is problem number 10. So find the multiplicity of r equals to kx comma y modulo by the ideal generated by x square comma xy. So kxy is equipped with the standard gradation where degree of x and degree of y is 1, and x square comma xy ideal generated by this is a graded ideal. So this quotient is also graded ring, or we can take is a graded module over xy itself. So we can talk about the Hilbert series and multiplicity. So we need to find the multiplicity of this quotient ring. So one can do this by Macaulay 2 also, but here I will do it by hand. So recall that if M is a finitely generated graded module of full dimension D, then its Hilbert series HMT can be written as some q of t divided by 1 minus t power d, where this q of t is a Laurent polynomial and q of 1 is not equals to 0. not equals to 0, not the thing, and it is positive. So this is one theorem from the lecture. So I am just recalling it. And also recall that also this multiplicity, the multiplicity of m, which we denoted it by e, the d minus 1th Hilbert coefficient of m, this is same as, so we denoted this by q m of t. So this is q, this will be dependent on m. So q m of t, the multiplicity of m will be same as to take this polynomial and evaluate it at 1. So if we can find the Hilbert series and we can find this polynomial q, then we can find the multiplicity. So let's try to find the Hilbert series of this quotient ring. So we will find the Hilbert series of R equals to kxy modulo the ideal generated by x square comma xy. Now Hilbert series of this R is basically summation the dimension over k of the nth component times t power n. So we need to find the nth component. So what is the nth component of this thing? So we can write R as, so this ideal, its generators has degree 2. So 0 degree and 1 degree terms in the quotient will be same as 0 degree and 1 degree term of kxy. So it is just k. It is the 0 degree term. Okay, so I should write. So R is basically R0, direct sum R1, direct sum R2, and so on. And we need to find these homogeneous components. And 0 degree component is clearly A. And the 1 degree component, it is just K x bar, direct sum K y bar. And in the quotient, x square bar equals to 0 bar and xy bar equals to 0 bar. And all the terms which involves x square and xy bar will be 0. So in degree 2, what will be survive? In degree 2, in general, we have x square bar, x bar y bar, and y bar square. So this will be 0 and this will be 0. So we will have only k y bar square. Similarly, for degree 3, so for degree 3, we have x q bar, x square y and xy square and yq. But these terms involves xy. So this will be 0 and x square is 0 means xq is also 0. So we will have only k y bar q. And you can check that for higher degree terms also we will have only one term. So this is basically k direct sum k x bar direct sum k y bar and direct sum with k y bar power n, where n is greater equals to 2. So the Hilbert series is the dimension, this dimension is 1, this is 1, so 1, and component of this is component of t power 0. Now component of t, is dimension of this. So this is 1 plus 1, so it is 2. Now component of t square onwards, we will have only one term. So this is summation t power n, n is greater or equals to 2. So this is the Hilbert series. Now we need to write the Hilbert series in this form. So how to do this? So this can be written as t plus uh, 1 plus t square plus tq plus so on. And this can be written as t plus summation t power n, n greater or equals to 0. And if you recall the formula, this is t plus 1 by 1 minus t. So if we add this, this is t times 1 minus t plus 1 modulo 1 minus t. So this is same as 1 plus t minus t square divided by 1 minus t. So this is the desired form. So that means q r of t, which is the numerator, this is 1 plus t minus t square. So hence the multiplicity of r is qr of 1. This is 1 plus 1 minus 1, which is 1. So this is the way you can try to solve the problems of this type, or you can use the Macaulay tool. That will be more easier, but by hand we can do in this way. So I think we have done enough problems for week 10. So it's a good time to stop here. So again, we will meet for the week 11.